This is my Ben Eater style 6502 computer that I've been working on. And it has the single stepper debugger board that I built and demonstrated a couple of videos ago. I've added a new feature for this, which is kind of interesting. Um, pin pin 2 on the 6502 chip is called ready. And if we look at the data sheet for the 6502 for the ready pin, which I said is pin 2, we can see that you can use the ready pin as Ben Eater does with his, when he attaches his world's worst video card to his 6502 computer, that you can use it to force the microprocessor to stop and do nothing while the ready pin is low. And when it goes high again, then it will continue to operate. And so that's one way to use it. However, it has another feature, and that's this. The wait instruction pulls the ready low signal, pulls the ready pin low, signaling the wait for interrupt condition. Thus, the ready is a bidirectional pin. So what's nice about that is that means that when we've created a break, that is a wait instruction, then that pin will go low. So what I've done is I have wired pin 2 to an LED, and so I've got a 1K resistor that starts at the 5-volt power bus, goes to this LED, and then the LED is wired to the negative side of the LED is wired to the ready pin. And in this way, I can set it up so that when I run something, yeah, you can see when the ready pin goes, it means that it is waiting for me to push the RQ button here to make it go. So here I've got it running, and here I'm just doing a memory test, and here it's telling me values that it's using for the test and the memory locations that it's testing to. And so that doesn't go too slow. I don't do every memory location. I only tell each page. That's why these two are always 0. So here you can see it's counting up, and when it gets to FF, that's the last of the test values that I use. And you can see that the ready light is on. It's waiting for me to press the interrupt button here to make it continue. So if I do that, it'll continue on. And here you can see that it's giving me some error reporting that it's found a problem. And it has lit the ready pin waiting for me to press another button. And so you might wonder, what am I doing here? I'm actually running a memory test, because what I've done, and I'm going to disconnect the power here a minute so I don't damage anything. But what I've done is I've actually wired in the 2 memory chips that I talked about in my last video. So here I have wired up 2 additional 32 kilobyte memory chips. And I can address either of these chips. And how I'm doing that is that this is a 74 HCT 138 address decoder, and I have this wired up. Let's look at the data sheet for the 138. So the 138, the 74 138 decoder has 2 gating pins. 2 that make it active when the gating pins are low, and 1 that's active when the gating pin is high. And when these 2 pins are low and this pin is high, then the address at A, B, and C will determine whether Y0 through Y7 are set low. So these will all be high whenever either the gating pins are not set correctly, and whichever pins are not set by the address. So if you have, for example, G2A high, then all of these pins will be high. But if you set G2A low and G2B low and G1 high, then if you select address, say you put all these low, A low, B low, C low, then Y0 will be low, and Y1 through Y7 will be high, and so forth. If you do A low, B low, C high, then say if you do, A low, A high, B low, C low, then that would select Y1, for example. So all all low, Y0, A high, the rest low, Y1, and so forth in a binary fashion through Y0 through Y7. I have that wired in the following manner. You can see that this yellow wire is attached to gate G2B, which is active when low, and that wire runs up through here, and up to the 6522 chip. It's active low gate, which is then tied up through this pin here, which this pin is the output of when A15 is low and A14 is high. Then since this is a NAND gate, this output will be low, and that will activate the 6522 if its other input gating pin is high, and it'll also make this pin low on my 74138. I have this pin tied. This is the positive gating pin that's tied to pin 12. So only our address A12. So only when A12 is high will this pin be active. And then finally, I have the other pin. The other gating pin is gated through pins A13, so that needs to be low. So that means when A15 is low, A14 is high, A13 is low, and A12 is high, then this pin is addressed. Then this chip will be addressed, and so this is addressed. This will be addressed at anything in the 5,000 range. Now, I also wired up the address lines. I didn't wire them up to A0 through A2. I wired the addresses from A4, A5, and A6. And the reason I did that is because in the 6502 computer, Ben Eaters, if you hook up the UART controller to his computer, he's got that oscillate address. He's got that wired up to address 5000 through 5003. And I don't want to interfere with that. I want to make it as easy as possible to remember the address. So what I did was I ignore the lower addresses. So you can use those addresses to connect to the UART, and that won't interfere with this chip, because this chip will only output, you have to use this chip to address, you have to use this chip if you hook up the UART to connect to the gating of the UART rather than the way it's currently gated. But if you gate it up so that the output Y0 gates the UART chip, then you can use this chip to gate it, and so then it won't interfere with the UART. Because I've got this set up right now, I'm only using one output from the 74138 decoder, and that output is Y7. So this way, if you address 5007, then you will activate this pin, which is connected to this latch. Now this latch is a little different than the one I've been using. I've been using the 7437 HCT374. This is a 74 HCT574. Electrically, functionally, it's identical. It's a D-type flip-flop that has an output enable, and it has a clock, and it's triggered on the positive going edge of the clock, just like the 374. The difference with this chip is that it has the outputs and inputs arranged more sanely. So if we look at the data sheet for the CD74 HCT574 versus the 374, you can see that in the 374, the inputs are kind of mixed in with the outputs. So here's D0 input, the Q0 output, the D1 input, the Q1 output, and they're all kind of mixed in with each other. And it's much easier to have it if they're separated out. So with the 574, all the inputs are on one side and all the outputs on the other side. The only thing that's not so nice is the inputs and outputs are on the opposite sides that I'd like them to be. which is why I did something that's very rare for me. And I flipped this chip around 180 degrees. You can see there's the notch for pin 1. So this is pin 1. These are all the inputs. And you can see the power is over here at pin 20, and the ground is over here at pin 10. And so these are all the inputs. And I have the output enable on pin 1. Which is you can hardly see it, but there's a ground wire there, and that's wired to ground. So this output is always enabled. And for the output, I've got D0 and D1 are wired into the upper addresses of this would be the D13 and D12 addresses of this transceiver chip. This is a 74HCT245 transceiver chip. This is a tri-state transceiver chip. And you can see that I have the output enabled, wired low. Sorry, this is the direction pin. The direction pin is wired low, which means data will go from B to A. This is the B side, and this is the A side. And then I have the high order bits, 2 high order bits wired. 12 and 13, A12 and A13 are wired to D0 and D1 respectively on this D latch. Now pins D6 and D7, all right, are controlling which of these chips is enabled, along with the output of this 138 address decoder. And I described this one in my last video, but this address decoder determines whether we're in the address range for the video RAM. And so you can see that, for example, when this address decoder is in the appropriate range, this line goes low, which is wired into this line here, which runs to the output enable for all 3 of these transceiver chips. So this is the address low order transceiver chip, this is the address high transceiver chip, and this is the data transceiver chip. And they're all wired together. When this is low, that means that we're in the address range of interest, and so we can enable the outputs of these transceivers. And you can see that, that these are all wired together through these yellow wires here. And that one goes to pin 1 there, and this goes to pin 1 of this transceiver, and this goes to pin 1 of this transceiver. Now, we also have to enable the chips. And so how I'm doing that is let's take this for example. If this pin is low in the data register, and you can see that if this is the input of an OR gate, and this is also low. If this is also low, this is the address decoder. So if we're in the right address range, and if this pin is low, then both of these are low. And so the output of this OR gate, which is here, will be low. And that output is wired here, over here to this AND gate. And this AND gate is just wired currently through the other input of this AND gate is just this resistor that pulls it high. And so the output of this AND gate will be high. Or sorry, these are, if either of these is high, the output will be high. But if it's low, then the output will be low. So if this or this is low, then the output will be low. So I'm using an OR gate here and an AND gate here, but I think of this as an AND gate and this is an OR gate because I'm working with negative logic. In other words, I've got negative input signals and I've got negative output signals. And so if both negative input signals, only if both input signals are negative, then the output will be negative for an OR gate. So an OR gate is like an AND gate for negative signaling, and the same thing, an AND gate is like an OR gate for negative signal. For negative signal is like an AND gate is an OR gate for negative signaling. If either is low, then the output will be low. So that's like an OR gate. Now the reason I have this chip here is not obvious, but the reason is because this is how I'm going to be determining, or I'm going to be selecting the output enable for these RAM chips, video RAM chips, when the video card is wired to them, which it isn't currently. And that's what these transceivers are going to be for, is for wiring in the video card. So when that happens, then this resistor will be replaced with wiring to the display interval output from my video card. So when the display interval is output. Actually, it'll be the blank interval, because when the blank interval is low, then that means that we are in the display interval. And so this signal will be low. And if it's low, then these are selected. Or if we've selected it from the computer, that it's selected. So that's how these chips get selected. So that's why I'm using an AND chip here. So you can see then that we started working out the logic from this wire, and we see we've gotten the signal down through to the output from here, which is the output all the way down here to this, which is going to be the background RAM, the background video RAM. If we work out the wiring from this one, it works the same way through all of this, but it'll end up going through to this output, which is connected to the output enable and the output enable and the chip enable. I keep saying output enable, but really it's the output enable and the chip enable I've wired together for these chips. So the output enable and chip enable are wired together, and it's controlled. That one's controlled by this output address. So by writing to this register, I can control which of these two chips, if either. I can make them both not enabled. I can make one or the other enabled, or I can make them both enabled. And you wouldn't want to do that when reading, but that might be convenient for writing. We could write the same value to both chips at the same time by making the write enable, making both of these pins low. Now, you'd want to be very careful not to do that when reading, because then you would get bus contention between these two chips, and who knows what you'd get. So that'll be up to software to make sure that that doesn't happen. If you recall, I wired the address chips here, and so I'm calling this this is the block selection. This selects which 8K block of the appropriate chip, and these outputs I'm calling bank selection, because am I getting this bank of memory or this bank of memory? So that's bank selection there. All right. So the question is, does it work? So first thing I want to do is I want to wire up some way to know something about what's going on. So I'm going to take one of these 8-segment LCDs, and I'm going to plug this in. I'm going to wire these up so that low is high and high is low. And that's so that I can, when a low signal, that's so that when a signal is low, I get the LED on. That's easier to remember. That means that something is selected. So if I look at, this is a 1K resistor array, and this is the common tie point here. So I'm going to plug that in here, like so. And I'm going to run a wire from here to the positive 5-volt bus. So now current will flow through here when anything on this side is low. So what we want to look at is, first of all, I'd like to know which bank of RAM is being selected. So let's wire from, let's see, this is the output here. This is the output here to enable the system RAM. So let's connect a wire from there over to here, and that should light up when the system RAM is being selected, is selected when we're reading or writing to system RAM. And so let's do the same thing for the other RAM. So let's just write to, there's the foreground RAM. And let's see, another. Pick up for the background RAM. So let's tell us when the background RAM is selected. And then let's just make sure that we're writing to this latch, because I haven't really tested this latch. Well, I mean, I have, but you don't know that. So let's wire up something from the latch. So let's do it in order, actually. Let's start with these. So here's the address line. So here's the low order of the two address lines. I'll just wire that to the top here. Oh, but the interesting thing about these is, I want to use green for that, actually. This is an address line. I like green for address. The thing is, this now is going to be, when this is high, then this will be high. I guess that's all right. Yeah, when this is high, then the light will be off. That's the problem, because these are positive signals. So let's do this. Let's move this guy Let's turn them over. Let's plug them in like so. And now we can do something different with these two. Okay, so let's get a 1K resistor to ground here. And another one we'll wire to ground. I did this one wrong. All right, so then we'll wire the address lines up to here and to here. Those will go high when the address is high. Then let's wire, actually I'd like to see the output of these, so let's wire these next. So this will be the outputs of the, so these are the 4 bits that we're using of the latch, and those are wired to the first 4 LEDs here. And then let's select the bank selection. So this is, we'll skip that LED. We'll skip this LED here, and we'll just wire this. This will be to the system when the system RAM is selected, and then when the here we go. When the foreground RAM is selected, that'll be the next LED, and when the background RAM is selected, that'll be that LED there. Move these down here so we can see them better. Can I get that out of the way there? Okay. There, now you can see that. All right. So I've written code that will run through and do a memory test. And how it works is I have a number of test values. I cycle through 0 through FF for the test values. But while circling through 0 through FF, the value that's actually stored at a memory location, I take the value 0, 1, 2, and so forth, and I add it to the low order byte of the address that's under test. That way consecutive bytes won't have the same, consecutive addresses won't have the same value in it. They'll have different values. And that will be testing, that'll help test basically the data lines and the low order 8 bits of the address at the same time. Oh, I forgot to mention one thing before we go on this. This orange wire here. This is the read-write signal from the CPU. And we need that to be buffered as well. And the reason we need that buffered is because if we just wire this in directly to the video RAM, and the video card is reading from the video RAM, but we've got the write signal. We're trying to force write low on the onto the video RAM, then that would be a problem. So what I'm doing is I am feeding it through to here, and then it's wired to the 2 chips you can see there. And here I have them pulled high with a 4.7K resistor. And so that pulls this, the read-write chip pin on each of these chips high if the transceiver is turned off. If the transceiver is turned on, then of course it'll get whatever it'll force it to whatever value is on the input on the B side here of the transceiver. So that's that, and it's convenient because these chips are 32K, so then they only need 15 address lines. So I can use A15, the 16th address line for the read write, and that gives me enough bits with 3 transceiver chips. Okay, so now let's run the test and let's see what happens. So first thing I'm going to do is I'm going to run through the system RAM, and I'm going to run through the system RAM starting above the stack. So starting at 0200, and I'm going to run that up to 1E00. And the reason is because I have some variables in upper memory and I don't want to overwrite them while I'm trying to do this. So I'm not testing all the system RAM, but I'm testing most of it. So let me plug in the power. Hit reset. And there we go. So you can see that it's counting up through the memory, the values. And here I'm displaying the memory location that it's at, but I'm I'm not doing it every memory location, only once per page, because otherwise this would slow it way down. And I'm counting up through memory, doing these tests. And if there's an error, it'll report on this top line. And you can see that it got through there and there were no errors. And you can see now that my LED is lit, meaning this is the ready light is lit, meaning it's waiting for me to push the IRQ button. And here you can see the memory that's selected. You can see that I have some items selected in. You can have one of these LEDs is selected, telling me which bank I have coded for communicating with next. So what I did was I'd actually set up this register with output values for this wait. If we run this again, I just want to show you that here you can see this LED is it's dim because it's blinking on and off rapidly, but this is because it we're jumping between ROM and RAM as we write to the read and write from the RAM. But this chip is lit. This LED is lit because the system RAM is what's under test. And so when that's done, I then program I program the output of this register to go to the lowest order bank to start with. And so these two LEDs are off. And I also test it, tell it to select this bank, which I believe we decided was the background memory. So this is the is that right? Sorry, yeah. So this pin here, which we decided was the background memory. So that's what's going to be under test next, is the background memory. And of course, nothing's selected yet here because I'm not yet reading to it. I'm sitting here waiting here with, you can see the ready pin is high. So it's waiting for me to press the button. And it's not working. Let me run through it again. Now it's waiting to press the interrupt. And here you can see what it's done is it's reported an error. It found an error at a memory address 2080. This is counting the errors. That's the first error. And the problem was that it was expecting, because you can see that you can compute this. This is the test value is 00. And the address is 2080. So we expect the output to be 80 plus 00, which is 80. And the C stands for computed. This is the computed output that we expect. And the R stands for read. This is what we actually read. We read 00. So it's not working. We can press the button and you can see it's continuing to have a problem. 01, it computes 81, it's reading a 01, and 02 and 03 and so forth. So this, I'm looking at this tells me that the eights place, in other words, you got 1, 2, 4, 8. So basically the D7 pin is not wired up, or perhaps it's a problem with the address. It could be that the A7 pin is not wired up. So we need to check that. And I mean, I'll be honest, I did run through this before, and I have already figured out what the problem is. But I wanted to show you how I went through that process. So I haven't fixed the problem yet, but I do know what it is. Okay, so what I did was I went through here to test. Let me turn off the power. So I've got my continuity tester. And I went through and I tested each of these pins. So here we're going to test the pins. So D7 to D7. So that's connected. D6, D5, D4, D3, D2, D1, D0. Okay, so we know that this wiring is all correct because it's running all the way through everything and it's connected. So now we're going to check the output of this transceiver to the memory chips, and we're in the background memory, so we'll check it down here. So here's D7, D6, D5, D4, D3, D2, D1, and D0. So those are all corrected. And we really only suspected D7, but I wanted to check them all anyway since I've got this tool out. And I want to make a point. I made a point in my last video that you could wire these up any way you want. They don't have to be wired. You could wire the data and address lines. You could mix them all up in the RAM and it'll still work because it doesn't know that you mixed them up. It just knows this address was specified. And so I'm going to store the data in this address. And now when I read it, same address is specified. And so I'm going to read it out. It's like you've switched everything up on the way in to the chip, but then when you read it out, it switches it all up back again, get out the same thing. But you can see the value of wiring them up the way it's labeled on the data sheet, because it would be very difficult if these were all mixed up to know which is D0, which is D1. So I do recommend wiring it according to how the data sheet shows, with D0 here up through D7 here, for when you need to debug, like you're going to wish you had done it that way. That's my recommendation. All right, so that isn't the problem. So maybe the problem is with the address chips, the address wiring, and 0, 1, 2, 3, 4, 5, 6, 7. See if these are 0, 1, 2, 3, 4, 5, 6, 7. Okay, so these are connected to each other. And I can check D7 here on the, with D7 on the, 0, 1, 2, 3, 4, 5, 6, 7 on the CPU, and those are connected. So that doesn't seem to be the problem. And then I look over here and I notice, oh, look, the output here, this isn't connected to D7 for some reason. And I know this looks contrived, because why in the world would I connect the output enable, the output of one of this transceiver chip to this one? Like, that makes no sense. But I assure you, I am fully stupid enough to have made that mistake. And I did make that mistake. That is actually what is the problem. So now I'm going to try to fix this, and I have not tested this fix. So let's see what happens. I'm going to pull this wire out, and I'm going to get an address line wire, which I did have ready to go because I knew this was the problem. And this should connect from D7. And I can't really get into these, so I'm going to connect it over to D7 over here. 0, 1, 2, 3, 4, 5, 6, 7. All right, and then so that we don't have to wait through the system RAM, which tested fine, I'm going to rewrite my code to skip the testing the system RAM. So here we go. Here's where it tests the system RAM. So I'm just going to say jump.video RAM. This will jump right over the system RAM to the video RAM. So let's program our chip. So we need to compile it. And I found a new way to speed up output so I don't have to write to the whole chip, since I've only changed the first set of items. I was doing that with the compiler, but now I don't do it with the compiler. I do it with my write. So I rewrote my write ROM program so that you can, let me get the help. I rewrote it so that you could specify the number of bytes to write, the offset from the start of the file to where you're writing, and the starting memory address on the EEPROM. So you can write any section of address up to, well, within a half a page. It does 128 bytes at a time. So, so I'm going to write ROM a.out, but -b, and you see there's 295 bytes here, so I'm just going to write 512. Good enough. And we're writing it. Oops. Okay, we're writing to it. And you may notice that I no longer have my handy 0 and searching for a socket here. This socket started to go flaky, so I had to get rid of it. I have some better ones on order. I'll let you know what I think of the new ones. They're gold plated. I'm hoping they'll last longer. This one's still working okay, so you can still use it. And let's start it up again and see what happens. Okay, so that's done programming. So let's pop this back in. All right, and we let's get this out of the way. We push the reset, and now we're waiting. We're waiting for this wait instruction right here. So we'll push this button. And now we're running through, and we'll see that this is interesting. So it did get past, it was at 2080, and it made it to 20FF. And it makes sense. It says it's expecting a 00, which the computed is 00, because there's the value is 01. So we made it all the way through the 00 value to the 01 value. And we got to 2FF. You can see that's the first error. I press the button again. You can see it stopped at 21FF, and it's again expecting a 00, and it's getting an 81 instead. And you see that basically every page, when it gets to the top address of the page, it's getting an 80 instead of a 00. I'm just going to keep going until we get to something different here. This is still doing the same thing every page. 37, 3B, C, D, E, F. Okay, and F, E. So now we're in value 2, and we made it all the way to 3FFE, and we've got the problem that it's expecting, FFE plus 2 would be the expected value of 0, and again, I'm getting an 81 here. Instead of an 80, it's an 81. And we run again, and we see at 26FD, value 3, it's expecting a 0, that computes to a 00, and instead I'm getting an 81. Seems to be something happens whenever it gets, not every time, but occasionally when it gets to a point where it's expecting the 00, it gets 81 or 80 in its place. Here's FD plus a 3, and that would be you would expect that as a 00, and I'm getting an 81. Made it up to 2A, FD, so it's going 2B, 2C, 2D, 2E, 2F, page 36, FD. Yeah, okay. So this is all kind of, oh, but no, this is interesting. Instead of an 81, I'm getting a 01 here. There's value 5, FB, B, C, D, E, F, 0. Yeah, so you expect that to be a 0, and it's 81. All right, so I don't know what's going on with this exactly, but I've got it sort of working, but obviously every now and then it doesn't want to see if it's consistent. Reset it and run. Yep, same thing. It's doing the same thing. There's the 80. Oh, that one's 81 because it made it all the way through 21. Yeah, it's interesting. It's 0 the first time. Nope, that time it's 81. It's not, oh, because it made it, depends on whether it stops with the Z1, the V1 or V0, the value, the test value being 0 or test value being 1, I guess. No, that's still an 80 there. Very interesting. The only thing I can think of is that this is a time when addresses change significantly, like from FF. I don't know. Doesn't explain it because if we get up to higher values, now it's at FD. All right. Well, I'm going to have to explain that in another video, but you can see I've got the video wired up. It's nearly working. I've got a test system to figure out if it's going. We can also watch here. You can see that it is addressing this higher order memory. It's just blinking. I don't know if you can see it on the video, but this LED is blinking, showing that it is addressing that RAM, the background RAM. Tell you what, let's change it so we look at the foreground RAM and see what happens with that. So in my code, I can just change this to select the foreground RAM first instead of doing the background RAM first. All right. Then we can compile that and write it. At least then we can see if we can address the foreground RAM as well as the background RAM. Here, I'm popping it back in. And yep, you can see well, there it's addressing, yeah, you can see the system memory is being addressed, but also, yeah, there you go. Occasionally background memory is addressed there. So here we got a point where it's running pretty smoothly. It's not, you can see it's counting up here, and there it finally got to an error. So that's pretty good. So we can address the foreground RAM and the background RAM. We got some problems with not reading some data right. I'm going to show you something else too that's interesting. You'll notice that I'm running this at 5 megahertz. Let me put the code back so it tests system RAM again. Let me get rid of that. And so now it'll test the system RAM. Compile. Put that chip in there. Write that. It wrote it. All right. Pop it back in here. So when I run, when I have it test system RAM, come on. Oh, so no, there it is, testing system RAM, and you can see it's fine. But if I change this to 10 megahertz, you can see that we get error, and it's almost always in the same place, 4FB. I'll reset it again. And you can see it's, there's 4FF, so slightly different. And if we do this, we'll see that we get errors, and they're kind of similar to what we had before. The values are weird, but you see like DF was 0, so we would expect, why didn't it say, it should expect DF here. 9F it says. F7, yeah, that computes right. FF, this should say FF. So that's very strange. But anyway, running at 10 megahertz, it doesn't work very well. But I bought some of these. Let's see if you can make that out. So this is a, come on, thing, focus. There we go. This is a AS7C 256 B. There you go. That's good. AS7C 256B-15. So this chip here, instead of taking 55 nanoseconds, this is a 15 nanosecond chip. So let's see what happens if we pop out our 55 nanosecond RAM. Let's see if you can see that. See that -55? We pop in the -15. This hasn't gone in before, so give me a second. There we go. All right. That's in there. So let's see what happens if we run this with a faster chip. And here we go. And it's not running at all. Chip in right? That's working. 10 megahertz. And there we go. Running at 10 megahertz. Using the faster memory chip. So it could just be that because of signal delays caused by all of this to enabling these chips, that maybe I'm just going to need slightly faster chips. So didn't like me fiddling around there with it. So that's looking pretty good. I'm going to investigate that. Thank you so much for watching this video to the end. If you're interested, I will go through the software that runs this this test if you'd like. Here you can I made it all the way to 1E00 and all 256 test values without any errors. So these higher speed chips might be key. It's kind of nice that they're narrower too. That gives you a little more room on the breadboard. They do cost more. This is quite expensive. I do have an 8K chip that's about the same price as I have an 8K 15 nanosecond chip that's about the same price as the 32K chip, but it's not quite pin compatible. What's address 13 here is used as an additional output or additional chip select, a positive chip select pin. So you can't, I couldn't just pop that in as a replacement. I have to rewire A13 here because well, this chip, well, the memory doesn't need it here because it's not reading memory that high. It does wired through here on my board to some of the other things. So I would need to rewire this. So anyway, this is a little bit more expensive, but you know, it's almost 4 times faster. Thank you for watching my video this far. I really appreciate it. If you like what I'm doing, it really helps me out if you subscribe or click the like button. And I really hope that you'll be here for the next one. Be sure to let me know if you want to see how the software, the memory test software works. Otherwise, I may not bother to put a video on that. And I will talk to you again real soon.